channels to the cores that require less data. That means reconfiguring compression, rerouting the scan channels, regenerating patterns, and this is a lot of effort. So you're dealing often with have to make a compromise between effort and test time. Furthermore, we also see that the pin-muxed approach is not very effective when we deal with large numbers of identical cores. You can broadcast scan inputs to multiple cores, but typically have to observe all of the scan outputs for all of the cores. And there's also some challenges associated with multiple different pipeline stages, different number of pipelines for the different cores. The throughput also is determined by the core shift speed. So even though you have a tester that can operate at a higher frequency, and even though your IOs can operate at a higher frequency, your shift
The pace of digitalization is unprecedented, and it's completely transforming our world, harnessing new technologies across the landscape of industry to fundamentally change the way we live. Electronics will be pervasive as companies move from selling hardware to providing personalized digital services. IoT will connect everything with automation and intelligence to optimize performance. It's all enabled by digital threads that turn silo data into connected disciplines and processes. These threads form the neural network of a digital twin, a virtual entity which mirrors the physical world, turning data into insight to continuously design, build, and optimize throughout.
안녕하세요. DFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise 스캔 어프로치인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
First, let's review some of the challenges we see in SoC designs today. The most common way of connecting core-level scan channels to chip-level pins is through what we call a pin-muxed approach, where MUX network decides which cores that are directly connected to the chip-level pins. This is straightforward for a small design like this, but when the number of cores grows and when the complexity of the cores grows and when we get multiple levels of cores, this becomes more and more complex and sometimes suboptimal. And the reason for that is a lot of the constraints that we have to deal with. For example, how many cores you can test concurrently is determined by how many IOs you have available for a scan test. Also, which cores that are tested concurrently or which cores can be tested concurrently is a hardwired decision. It's something you have to decide during the design process. There's also dependencies related to the number of channels at core level, and that also again determines which cores you can test in parallel. And now you can build in some more flexibility.
안녕하세요. TFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는
The pace of digitalization is unprecedented, and it's completely transforming our world, harnessing new technologies across the landscape of industry to fundamentally change the way we live. Electronics will be pervasive as companies move from selling hardware to providing personalized digital services. IoT will connect everything with automation and intelligence to optimize performance. It's all enabled by digital threads that turn silo data into connected disciplines and processes. These threads form the neural network of a digital twin, a virtual entity which mirrors the physical world, turning data into insight to continuously design, build, and optimize throughout the product and production lifecycle. This transforms siloed electronic systems development, enabling intelligent simulations and parallel design to front-load quality control. Synchronizing data throughout the supply chain and manufacturing process improves productivity and allows manufacturers to diagnose potential obstacles and avoid them. An integrated lifecycle with requirements, planning, and execution in a single system allows complex products to be developed faster and with a full collaboration of all stakeholders. Siemens can help you achieve rapid digital transformation, powered by the world's most comprehensive digital twin. There's no need to dream about the future. It's already here.
안녕하세요. TFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는 No Compromise Scan Approach인 테센트 스트리밍 스캔 네트워크를 소개해 드리고자 합니다. 본 웨비나는 테센트 프로덕트 매니지먼트 디렉터인 가이어가 진행하게 되며 한글 자막이 제공됩니다.
First, let's review some of the challenges we see in SoC designs today. The most common way of connecting core level scan channels to chip level pins is through what we call a pin-muxed approach, where MUX network decides which cores that are directly connected to the chip level pins. This is straightforward for a small design like this, but when the number of cores grows and when the complexity of the cores grows and when we get multiple levels of cores, this becomes more and more complex and sometimes suboptimal. And the reason for that is a lot of the constraints that we have to deal with. For example, how many cores you can test concurrently is determined by how many IOs you have available for a scan test. Also, which cores that are tested concurrently or which cores can be tested concurrently is a hardwired decision. It's something you have to decide during the design process. There's also dependencies related to the number of channels at core level, and that also again determines which cores you can test in parallel. And now you can build in some more flexibility in this approach with a more complex MUX network, but that also increases the potential for routing congestion related to routing all of the scan channels all across the design. Now there are also different ways you can deal with this. Now you can implement what we call a bottom-up flow, where you allocate a fixed number of scan channels like early in the flow. Let's say you decide to have the same number of scan channels for all of the cores and kind of make a lot of decisions early. That's the easiest approach, the least effort. But a side effect of that, you might end up wasting bandwidth because the different cores that you group together end up having different scan chain length or different pattern count. Now you can address that then by reallocating the scan resources, for instance, allocating fewer scan channels to the cores that require less data. But that means reconfiguring compression, rerouting the scan channels, regenerating patterns, and this is a lot of effort. So you're dealing often with have to make a compromise between effort and test time. Furthermore, we also see that the pin-muxed approach is not very effective when we deal with large numbers of identical cores. You can broadcast scan inputs to multiple cores, but typically have to observe all of the scan outputs for all of the cores. And there's also some challenges associated with multiple different pipeline stages, different number of pipelines for different cores. The throughput also is determined by the core shift speed. So even though you have a tester that can operate at a higher frequency, and even though your IOs can operate at a higher frequency, your shift speed is limited by what the cores can handle. And as we see more designs using a tiled approach, tiles with abutment, where you don't have this top-level routing layer, it becomes even more challenging to route scan resources to the various cores, because you have to go through one core to get access to the next. Tessen Streaming Scan Network, or SSN, is a new approach to distribute scan test data across an SoC. In this example, we see a design with 6 cores and an SSN bus. The SSN bus is a high-speed synchronous bus to deliver packetized scan test data to the cores. Part of the SSN network is what we call a host node in each core. This host node ensures that the right data is picked up from the SSN bus and sent to the scan inputs of the core. Could be compressed, uncompressed, or a combination of both. And also ensures that the scan output data is placed back onto the bus. The host nodes also generate the DFT signals locally, scan enable, scan clock, and so forth. Each node knows what to do and when to do it based on a simple configuration step that's done over IJTAG. This means that the groupings of which cores are tested together and which cores are tested sequentially, which cores are active, these decisions are not hardwired. They are fully configurable. The configuration is done as a setup step, one-time setup step per pattern set. Once this setup is done, all the data on the SSN bus is payload. The fundamental principle behind SSN is that core level and chip level DFT is decoupled. What that means is that the number of scan channels per core is completely independent of the width of the SSN bus, and as well as the number of scan channels at the chip level, and also independent of all the other cores in the design. This means that dramatically simplifies the planning and implementation effort, and it also allows you to make grouping and other decisions at retargeting time rather than design time. This architecture is very flexible. The bus width is typically determined by the number of pins, scan channel pins available. It could be as narrow as 1 bit. This architecture also eases routing and time enclosure, since we eliminate the top-level test mode muxing, and it is also fully compatible with tile-based designs with abutment, since no top-level signals have to be routed. SSN also contains many capabilities that help optimize test time and test data volume without having to increase the DFT or planning effort. SSN has capabilities to automatically tune how much data is sent to each core to help reduce the white space in the test data, and also has a capability to test multiple identical cores at constant cost while still have diagnosis support. And SSN is also proven in silicon. So how does SSN work? Let's take a closer look at the concept of packets and packetized scan test data delivery. In this little example, we have a design with 2 cores, Core A and Core B. Core A has 5 scan channels, and Core B has 4 scan channels, 4 inputs, 4 outputs. Now, a packet is defined as the total amount of data that is needed to perform one shift cycle across all of the cores that are tested concurrently. So since we are testing both Core A and Core B, the packet size in this example is 9 bits. Now at the same time, notice that the SSN bus width is 8 bits. And remember that the width of the SSN bus is typically defined by the number of pins available for test, completely independent of number of scan channels per core. Now, on the left side of the slide here, we see how data is streamed through the bus, through the synchronous SSN bus. Now, let's take a closer look at the first packet. Again, notice that to deliver all of the data corresponding to that packet, we need 2 cycles. In the first SSN bus cycle, we see that we are able to deliver all of the data needed to perform 1 shift cycle for core A, all the 5 bits needed. And so after that first SSN bus cycle, we can shift core A. But core B has to wait because it's the rest of the data, all of the data needed to test core B isn't available until we have we're at the second SSN clock cycle. And the SSN host, the host nodes, then know exactly where the data corresponding to that particular core is on the bus, and also when to pulse the shift clock. Now, if we look at the next packet, notice that the positions now are shifted, rotated. Again, this happens because we are able to fully utilize, pack all the data together. And also now, since we have 9 bits per packet and an 8-bit bus, that's why we see this rotation. So on the like the bottom row here, notice that the first bit for core A in the first packet, it was on the very bottom. Now it has shifted for the second packet. So this rotation will continue packet after packet, and the same slots that we used for the scan input data is also used for scan output data captured from the core and put back on the bus, again delayed by 2 packets. So in a nutshell, this is how packetized data delivery works with SSN, and how the width of the SSN bus is completely independent of the width of the cores. As we mentioned earlier, SSN contains several capabilities that help reduce test time and test data volume. One capability is what we call independent shift and capture. Now, in many retargeting schemes, PinMux approaches, the capture has to be aligned. What that means is that if we are shifting in multiple cores concurrently, and these have different scan length, we have to pad some of the cores with the shorter chains and then perform capture at the same time. With SSN, we also do support aligned capture, but SSN, when we're testing cores independently, the DFT signals are generated locally, and the capture is independent across the different cores. And this allows us to have a more optimal pattern set. SSN also has bandwidth tuning. What bandwidth tuning is to, rather than shifting as many bits as there are scan channels per packet, to allocate fewer bits per packet to the cores that require less data. What that means is that for a core that, let's say, has requires fewer patterns, we allocate less data per packet, and that way we're able to tune the bandwidth and optimize the test time for the design. SSN provides a scalable method for testing any number of identical cores with a constant amount of test data at a constant test time. For identical cores, the compare circuitry is included in each host node. The data that is provided to the identical cores is the scan input data, expect data, and mask data. That allows SSN to do the comparison inside each course. The accumulated status is then shifted out on the SSN bus. This is the accumulated status across all of the identical cores, and a pass-fail bit per core is also captured in the host and scanned out through IJTag. The SSN interface is very flexible. We have already talked about the SSN bus width. Typically, that bus width is defined by the number of pins available for scan test. And the SSN bus can be any number of bits wide. It could be 1 bit wide. And even an existing SSN bus, let's say an 8-bit SSN bus, can be operated at a subset of that width. You can operate an 8-bit bus at 7 or 6 or 5 bits as well. Now, there are also a couple of other things related to interface flexibility that I would like to cover, just to demonstrate how powerful SSN is. One capability is what we call streaming through JTAG. This is a way to, rather than using the SSN bus for distributing scan test data, distribute the scan test data through the chip-level JTAG interface and the IJTAG chain, and simply bypassing the actual SSN bus. There are two reasons to do this. One is as a debug mechanism or a kind of survivability mechanism, where you can, if you suspect there are problems in the SSN bus itself. But this capability can also be used as a low pin count interface to deliver scan test data through JTAG. Another capability that I want to cover is time domain multiplexing. So SSN has the ability to change the frequency across the bus, and also change the number of bits across the bus, increase the frequency and lower the number of pins, and vice versa. There are a few different reasons why you want to do this, but one scenario is what's shown here, where you can have a different frequency on the chip level IOs versus what you have on the SSN bus, versus what's how this internal core level scan chains are shifted at. Now, in most PinMux applications, the limiting factor for shift speed is what the cores are capable of, right? So if your scan chains in the cores can't shift any faster than 100 megahertz, that's how fast you shift data into the chip from the tester as well. Now, with SSN, you can configure the design as shown here. You still shift at 100 megahertz at core level, but you can now distribute data across the chip at a much higher frequency at, let's say, 400 megahertz. Now, the reason you do this is that in most cases you have significantly more scan channels, so significantly more bits in the packet than the bus is wide. Then at the chip level, based on the IOs and the tester, it makes more sense to shift at let's say 200 megahertz. Now you could also, of course, also if you shift at 200 megahertz at chip level, also distribute the data across the SSN bus at the same frequency, but by multiplying the frequency, you can route a smaller, narrower bus across your chip, and that eases routing. Now that we are announcing and releasing SSN, it is after we have been collaborating with partners, with leading semiconductor companies for well over 3 years. We have engaged with our partners early in the process to ensure that by the time it is released, it is well proven and demonstrated in many different design flows. We have completed many pipe cleaner experiments, ensured that the product is compatible with many different flows. And we have also completed several tapeouts and demonstrated SSN in silicon. Some of our partners presented their results at an event that we held at the International Test Conference earlier this year. And at the same conference, we also presented a technical paper that was co-authored with Intel. In this technical paper, we describe in detail the SSN technology and how it works. So this is a good paper to look up if you are interested in understanding the details of SSN. And also in this paper, there is a case study that presents the results from Intel's evaluation of SSN, where they compare SSN to both their internally developed fabric as well as to conventional pin-muxed access. And the results here show that in all the different ways comparisons were done, SSN came out favorably. Also, if you want to learn more about SSN, we also have collateral such as data sheets and white papers available on our website. Now, if you are interested in SSN and think that you might want to leverage it for a future design, the one thing that I would encourage you to take a look at is what we call the SSN-ready design flow. So SSN leverages a lot of the automation that is available in our tools today, capabilities that you might already be using. And we have also built a reference flow that is described in the Test and Shell user's manual that you will see is very similar to the Test and Shell reference flow for hierarchical designs. Now, some of the things that SSN leverages is, for instance, IJTag. So IJTag is required. IJTag is used to initialize the SSN network. Clocking, now we talked about also how SSN is generating the clocks locally. So a standard OCC or a single entry clock mesh is required. Beyond that, there are several capabilities that many of our customers use today to leverage the automation in our flow, and these are also highly recommended in context of SSN, as it will make the overall implementation easier. And you can also read more about these requirements in the Test and Shell user's manual. Thank you for your time here at the DFT India Tech Day. I hope you've had a chance to learn about the silicon-proven test and streaming scan network and how you can leverage this technology to reduce your DFT development time and reduce manufacturing test time and volume.
안녕하세요. DFT 웨비나에 관심을 가져주시고 참여하여 주셔서 감사합니다. 이번 웨비나에서는
I hope you've had a chance to learn about the Shell user's manual. Here at the DFT India Tech Day. I hope you've had a chance to learn about the silicon-proven test and streaming scan network and how you can leverage this technology to reduce your DFT development time and reduce manufacturing test time and volume.